This podcast in Chapter 4 will talk about force diagrams for objects at a constant velocity on an inclined plane. The first thing I'd like you to think about are some of the activities that we've done in class. In class, we will be exploring a fact about objects moving at a constant velocity, and that's this. Objects moving at a constant velocity have a net force of 0. In other words, all of the forces on such an object will balance out. Let's look at this example. It says a penny of mass 2 grams slides down an incline of 30 degrees at a constant speed. Draw a force diagram for the penny and calculate the coefficient of kinetic friction for the penny. So I'll represent the penny with a rectangle. I'll draw the center of gravity, and from the center of gravity, I'll draw my first force, which is the force of gravity going straight down. Then I'll draw the normal force, which is perpendicular to the surface. And finally, I'll draw a force of kinetic friction, which is parallel to the surface, and which opposes the motion of the penny. The penny wants to slide down the incline, and friction will always oppose that motion. I'm just going to take a moment to look at these force vectors. Here's my gravitational force vector. I'm going to make a vector sum. I didn't do a great job with my normal force here. Normal force isn't quite long enough. I'm going to add to it. But these three vectors should create a vector sum of 0. What I mean by that is my starting point and my ending point are the same place. And because my starting point and ending point are the same place, that indicates a net force of 0. Now you've seen how even I, who have a lot of experience drawing these force diagrams, had a tough time drawing the normal force exactly the right length. Sometimes what we do to make it easier for ourselves is we draw in the components of FG. Now we have to be a little bit careful with this. Put this over also. There we go. We have to be a little bit careful with including the components of FG because the College Board does not like you to do this. They do not like you to draw in what I'm drawing in right now. They are afraid that you will think that these components of FG, the parallel and the perpendicular components, will be seen as separate forces. They are not separate from FG. They are components of FG. So we need to be careful about that. And when we draw the force diagram, you would not include those components. But for the purpose of explaining this problem, I am going to include these components so you can see what I'm talking about. F perpendicular is equal and opposite to Fn. So if I were to take Fn and drag it down, it would match up. And likewise, Fk is equal and opposite to F parallel. Now, since you don't have a smartboard, the way that you can indicate that is with a congruent symbol. Fn and F perpendicular go together, and Fk and F parallel go together. Okay, so I've drawn my force diagram, and now what I need to do is calculate the coefficient of kinetic friction for the penny. The definition of coefficient of kinetic friction is Fk over Fn. And you may remember that coefficient of friction is unitless, and it doesn't have a sign. So sometimes you'll see it drawn with an absolute value symbol around it because the sign doesn't matter. So I'm going to do some substituting now. I know that Fk is equal and opposite to F parallel, and I know that Fn is equal and opposite to F perpendicular. In a previous podcast, we saw that F parallel was equal to FG sine theta, and that F perpendicular is equal to FG cosine theta. And the FG's cancel out, and what we're left with is sine over cosine. Well, sine over cosine is just the tangent of the angle. Now my angle in this problem is the tangent of 30 degrees. And so the tangent of 30 degrees would be, or 1 over the square root of 3, or the square root of 3 over 3. So that would be my coefficient of friction.